All right, let's review solubility, precipitates, acids, and bases. So to understand solubility, you have to look at the solubility chart or the solubility reference material that is on your blue reference chart. Okay, on the back of it, it says solubility of common ionic compounds in water, and there's a whole list of compounds that are soluble with their exceptions, and there's a whole list of compounds that are insoluble with their exceptions as well. So refer to the chart, look underneath soluble, and when you look for NH4, it should be the second compound listed there underneath soluble. Okay, if I look over to the right, it says common exceptions, and there are none. So that means that NH4 is soluble in water, which means it will dissolve in water. Find NO3. NO3 is right below NH4 on the soluble list, on our solubility rules, and it also has no exceptions. So ammonium and nitrate ions are both soluble in water. They are always soluble because they don't have any exceptions, which means they will always dissolve in water. So let's figure out if the following compounds listed are soluble or insoluble. So starting with sodium nitrate. Sodium nitrate. So I'm always looking for the negative ion here, and the negative ion is my nitrate. So I'm looking for NO3 minus, and we just mentioned that was one that we just looked at. NO3 minus is soluble, and it has no common exceptions, so that means it is always soluble. It will always dissolve in water. Looking at sodium hydroxide, find the negative ion, it's hydroxide. So OH minus. So when you look at your solubility list, go all the way down to find OH minus. And OH minus is insoluble, but it does have exceptions. Its exceptions are compounds of ammonium, the alkali metal cations, calcium, strontium, and barium. Okay, so the alkali metal ions, that is group 1 in my periodic table. Group 1 are the alkali metals. And I know that sodium is in group 1. So sodium is an alkali metal. So that means it does meet the exceptions. It is an exception. So instead of being insoluble, it is now soluble because sodium is an alkali metal. And our last one is barium sulfate. So identify the negative ion. It's sulfate, which is SO4. So find that on your list. So if I look for sulfate, SO4, and go all the way down, I notice that it is on the soluble list. Okay, and its exceptions are compounds of strontium, barium, lead, and mercury. Okay, so this compound, or this element right here, this is barium. Barium is one of our exceptions. So instead of being soluble, it is now the opposite, and it is insoluble, which means it will not dissolve in water. This compound would form a precipitate. Alright, so what is a precipitate? Well, a precipitate is a solid that doesn't dissolve. So in other words, it's an insoluble solid. Insoluble means it does not dissolve in water. So in other words, if I mix two liquids together and a powdery substance forms, that powder is a solid. That powder is my precipitate. Okay, it did not dissolve in that compound, therefore it showed up as a solid. So I said two liquids, when I combine those forming a solid, The most common term for two liquids would be aqueous, because a lot of time we might think liquid would be water. Well, aqueous could be water, but it could be something else that is in the liquid state. So we typically use aqueous to describe the form that creates a precipitate. So how can you tell if a reaction is a precipitate reaction? Well, double replacement reactions are always going to form. Actually, I take that back. They're not always going to form precipitates, but a precipitate will always be formed from a double replacement reaction. So in other words, if I've got two compounds, an aqueous compound and an aqueous compound, and they form something that is also aqueous, and now I've got a solid, that tells me that that solid here is my precipitate. And I'm going to abbreviate precipitate PPT. All right, so let's figure out which is my precipitate in this reaction. So in reaction 1, I've got magnesium chloride, that is aqueous, plus sodium hydroxide, which is aqueous, produces magnesium hydroxide, which is a solid, and sodium chloride, which is aqueous. So I can identify the precipitate easily because I notice that I've got an aqueous solution here, an aqueous solution here, and it produces, from two aqueous solutions, it produces a solid. This is my precipitate. Okay, it formed a solid and an aqueous solution. So this is how you can tell what your precipitate is. If there is an S next to it, a solid, that tells you that two liquid or aqueous compounds formed a solid compound. That's my precipitate. So in reaction 2, I've got hydrochloric acid, which is aqueous. I've got sodium hydroxide, which is aqueous, producing sodium chloride, which is aqueous, and water, which is a liquid. None of these forms a precipitate. Okay, so this is not a reaction that will form a precipitate. So this one is a no, this one is a yes. Okay, because I did not form a solid in this compound. It's two aqueous solutions, just like we had up here. However, these two aqueous solutions did not form a solid. There's an aqueous there and a liquid there. Neither one of those are an S. All right, complete the replacement reaction and use the solubility chart. Okay, so I've got calcium chloride and sodium carbonate. So calcium is the positive ion. Chlorine is the negative ion. Sodium is a positive ion. Carbonate, my polyatomic, is negative. So two positives will never bond together. Two negatives will never bond together. So what ends up happening is that the positive calcium forms a bond with the negative carbonate, and the positive sodium forms a bond with the negative chlorine. Okay, we always list the positive ions first. So what you end up with is I get calcium and carbonate. Calcium has a +2 charge, and looking at your polyatomic list, if I go down to find carbonate has a -2 charge. So when I cross these two charges to figure out what the new compound will be, the 2 comes down here, the 2 comes down here, and the 2's are basically going to cancel each other out. So what you end up with is CaCO3 as one of my compounds. And my next compound, I've got sodium, which is in group 1, so it's +1, and chlorine, which is in group 17, which is a -1. And if I cross the charges here, bring down the 1, bring down the 1, so nothing changes. So Na +1 and Cl -1 gives me simply sodium chloride. Okay, so now figuring out which one is a precipitate. Okay, in this compound, you're going to find the negative ion. The negative ion was the carbonate. So when you look on your solubility rules list, go down to find CO3 minus 2, and it appears to be insoluble, and the exceptions are compounds of ammonium and the alkali metal cations. Well, calcium is close to group 1, but it's actually in group 2. So it's an alkaline earth metal. It's not an alkali metal. So this compound is insoluble, which means it is going to form a solid, which means this is my precipitate. Okay, sodium chloride, just to verify it, if I find my negative ion, chlorine, go down my list, I see Cl minus, and it is soluble unless it's forming compounds with silver, lead, or mercury. Well, it's bonded with sodium, which is not any of those exceptions, so that means that this compound is going to be soluble. So that will get an aqueous. Okay, so this is soluble. This one is insoluble, forming a precipitate. Let's look at our next one. Next one's barium nitrate plus potassium sulfate. So to help you find barium, barium is a metal, it's a positive charge. Nitrate is a negative ion. Potassium is a positive metal, and sulfate's a negative polyatomic ion. So the positives always bond with the negatives. So barium is going to form a bond with sulfate, and potassium is going to form a bond with nitrate. They're going to replace each other 2 times. So what forms? Well, when I get barium and sulfate. Okay, so if you find barium on your periodic table, you notice that barium is in group 2, so it's got a +2 charge. Sulfate is a polyatomic, it's got a -2 charge. And when I cross those charges, you get a 2 and a 2. Those cancel each other out. So I simply just get barium sulfate, BaSO4. And my next compound that's formed is between potassium and nitrate. Okay, so potassium, if you look on your periodic table, potassium is in group 1. So it's got a +1 charge. Nitrate is a polyatomic ion, and it's also got a -1 charge. So when I cross them, bring down the 1s, nothing changes. So it's simply KNO3. So let's figure out which one is the precipitate. So find your negative ion. So nitrate is my negative ion on your solubility list. If you go all the way down, we said nitrate was always soluble. Okay, always soluble. So that means that this is going to form an aqueous solution. Okay, anything that has a nitrate in it will always be soluble. So let's check barium sulfate. So sulfate is my negative ion on your list. Go all the way down to find sulfate, SO4 -2. It shows that it is soluble, which means it'll dissolve in water. It's aqueous, except when it forms compounds with strontium, barium, lead, and mercury. Well, here's barium. Barium is one of my exceptions. So instead of being soluble, it is the opposite. It is insoluble, which means this will form a solid. This is my precipitate. It is insoluble. So the solid indicates that it is my precipitate. All right, moving on to the back, we're going to talk a little bit about acids and bases. So identifying basic properties here. Starting with number or letter A, pH larger than 7. So anything with a pH greater than 7 is definitely a base. Anything with a pH less than 7 is definitely an acid. Electrolytes. Strong electrolytes could be strong acids. Strong electrolytes could also be strong bases, so that is both. Turns litmus paper blue. Remember, blue, B for base, which turns litmus paper red. Well, that's the opposite of blue. And as far as litmus paper goes, that's an acid. Which turns phenolphthalein pink? That is a base. H2SO4. It's got an H in the front of the compound. That's an indicator that this is an acid. NaOH. Anything with an OH like this is considered a base. This is a strong base. Okay. Letter I. This says the hydrogen ion concentration is greater than the hydroxide ion concentration. So we know that acids have more hydrogens than they have hydroxides. And J says hydrogen ion concentration is less than the hydroxide concentration. That means that indicates a base. Substances that are sour, those are acids, and substances that are bitter, those are bases. All right, so now let's name the ions. Okay, so an H plus is a hydrogen ion. But it's also referred to as a proton. Okay, so yes, we know a proton is in the center of an atom, but we call it a proton because it has a positive charge. So just remember that H plus is either referred to as a hydrogen ion or a proton. So it's got two names to it. An OH minus, this is a hydroxide ion. And the last one here is H3O. No, it's not water. It's a water with an extra hydrogen, and it is classified or known as a hydronium ion. So hydronium ions are also acidic. A strong concentration of hydronium ions represents an acid as well. Okay, so labeling the pH scale. Let's see here. Let's label the pH scale with things like acidic, basic, neutral, and the types of ions. Okay, so we know that 7 is neutral. We know that anything greater than 7 is base, a base or basic. We know that anything less than 7 is acidic. Okay, so the ions, let's do this in a different color. So acids have hydrogen ion concentrations, and they increase as I move to the left, which means they decrease as I move to the right. And bases have hydroxide ion concentrations, and they increase to the right, which means they decrease to the left. Okay? So strong acids and bases completely dissociate. There's that word, dissociate. Dissociate means to break apart or separate. And they're going to separate into ions. Okay? So label each box as a strong acid or a weak acid. When I look at the box on the left, I see that there's hydrogen ions and there are chlorine ions. Not a single one of these is bonded together, which means they have separated completely. This indicates a strong acid. Strong because it is completely separated. dissociated. When I look to the right, I notice I've got HCl, I've got H, Cl, H, Cl, and HCl. So these two compounds right here have not separated yet. So they are not ionized. So this indicates a weak acid. Okay, and it's weak because they have not ionized yet. All right, at the bottom, define acid-base theories. So a Bronsted-Lowry acid and a Bronsted-Lowry base. So Bronsted-Lowry acids donate protons. So they're going to donate or give away hydrogen ions. Okay, they're proton donors. So remember, H plus is also referred to as a proton. So they're referred to as proton donors. Bronsted-Lowry acids are the opposite. They accept protons. They accept hydrogen ions. So they are proton acceptors. Okay. Which type of acid or base is water in this reaction? So look at the reaction below, and I see HCl plus H2O produces H3O and chlorine. Well, I notice that H2O became H3O, and it became H3O because hydrogen was donated to water. So HCl donated a proton, and water accepted a proton. So those substances that accept protons are Bronsted-Lowry bases. So we're going to say that water is a Bronsted-Lowry base because it accepted a hydrogen. Okay, and the next one says, what is ammonia? Well, I've got sulfuric acid plus ammonia produces HSO4 and NH4. Okay, so NH3 became NH4 because it gained a hydrogen from sulfuric acid. So ammonia accepted a proton, so it is also a Bronsted-Lowry base. Okay, and the last part here, acid-base calculations. The equation for pH, according to our reference chart, is pH equals the negative log of the hydrogen ion concentration. Okay, so let's practice calculating. Calculate the pH of a solution whose hydrogen ion concentration is 1.7 times 10 to the negative 3. So this is your H plus. Okay, and it's asking me to solve for pH. So pH equals the negative log of the hydrogen ion concentration. So pH equals the negative log of, and I'm writing brackets, but your calculator shows up as parentheses, and that's okay, 1.7 times 10 e to the negative 3. And when I type that into the calculator, remember to use the negative symbol and not the minus symbol. If you type in the minus or the subtraction symbol, it will give you an incorrect answer. So the best answer with the negative symbol is a pH of 2.8. 2.8 is less than 7, making it an acid. Alright, so remember the following acid-base names and formulas. So strong acid, HCl is an example of a strong acid. Excuse me. HCl is hydrochloric acid. Okay, a weak acid, HC2H3O2. This is known as acetic acid. It's a weak acid. Strong bases would be NaOH. This is sodium hydroxide. So any compound that's got OH is going to be a strong base. And a weak base is ammonia. Ammonia does not have an OH, yet it is still a base, but it is a weak base. So one last thing that I want to show you, let's go ahead, actually we could write it down here at the bottom. One last thing I want to mention to you is a neutralization reaction. Okay, so a neutralization reaction occurs when I combine a strong acid with a strong base. Okay, so if I take an acid and I add a base to it, the two things that form are always going to be salt and water. Okay, so when you're trying to identify a neutralization reaction, you might not be able to identify a salt, but we should know how to identify water as either H2O, or it could be written or expressed as HOH.